Yes. Yeah.
Start? Yeah. Okay. Hello, everyone. It's my pleasure to introduce Samuele. He is an RLA postdoc helping our group. Samuele is a PhD from Jan Peter's group. He's an expert in policy gradient methods and robot learning. And I think he could go to any industrial lab, but instead he chose to come us to help our group, which shows his commitment to academia. And also, very soon he's going to join as a faculty member in Europe at the University of Innsbruck. So yeah, please welcome Samuele.
So thank you very much, Luca, for your kind introduction. So today I will present a gradient critic for policy gradient estimation, and my co-authors are Andrew, Marta, and Luca. And what I will tell you a bit more precisely in these slides is that classic policy gradients are Monte Carlo estimators. And for this reason, they are basically performing, or they are problematic in the off-policy setting. And I will present you an alternative to this policy gradient estimator, which consists basically in using temporal difference to estimate the policy gradient. So, why off-policy? So, to understand why I'm so interested in off-policy learning, we need to look back to on-policy learning. So, in the on-policy policy gradient, we consider a policy phi, parameterized by some parameter theta. And then with this policy, we collect some data. And then using the policy gradient theorem, we can improve our policy by a tiny bit. Once we have improved our policy, the policy will be different. And therefore, we cannot reuse the previous data to improve the policy. We needed to collect a new data set. And only then we can have another little policy improvement. And therefore, we needed to collect many, many samples and to do many improvement steps to hopefully arrive to the optimal policy. This is, of course, very expensive in terms of sample efficiency. And an alternative would be instead to have something like an off-policy gradient estimator. With this off-policy estimator, we can still start from a policy phi theta, collect a data set, use our policy estimator to compute the gradient, improve the policy, and then we can do our improvement many, many times, reusing the samples. And ideally, of course, this cannot happen in practice, but ideally arrive to the optimal policy by reusing samples. And so this schema is much more sample efficient. And I don't think that in reality there are truly off-policy algorithm or a very seldom complete on-policy algorithm. Most of the time, I think algorithms are somewhere in between. For example, we can have DPG, TD3, SAC that are a bit on policy, but not completely off policy. And the focus of 2 or 3 years for me of my research was to develop algorithms that they can deal with a large discrepancy between policy distribution. And so that I really believe that if you are able to take large distribution shift, then we can achieve sample efficiency. So to understand how to develop a policy gradient estimator, we need to look on what we already have. So the classic policy gradient estimators. The objective of policy gradient estimator is to estimate this quantity. So we have the gradient of the return with respect to the policy parameters. So in this equation, we can see a possible way of computing, or actually 2 possible ways of computing the policy gradient. So here we have the classic, let's say, it is the quantity that we want to estimate. Here it is the classic policy gradient theorem. So here you can recognize the discounted state distribution, and you take an average over this quantity. This expression is a bit less known, but you can believe me that it is basically equivalent to this other expression. There is just a proportional factor that is difference between the two. And here we can see basically this expression as an average over trajectories, that they must be on policy trajectories. And then we see that the gradient can be composed in summation of discounted terms. And these terms are composed by the Q function, the gradient of the logarithm of the policy. In the rest of this talk, we will focus on this expression. So we start from this expression, and we see that actually just doing a bit of renaming, we can call this guy G, and it comes clear that the gradient of the return is a summation of discounted terms. We call these terms immediate gradients, and these terms comes in sequence. So for example, we have a first immediate gradient on the state 0, then a gradient on the state 1, and so on and so forth. So they come basically from the interaction of the policy with the environment. And we suddenly realize that this gradient estimator is a Monte Carlo estimator. Basically, we are taking rollouts, summing discounted gradients, summing them up, and then obtaining our estimate of the gradient. We all know that Monte Carlo estimators have a high variance, so this is already something not good. But furthermore, they are also problematic in the off-policy scenario. So how we do now with the classic gradients estimators, it is either we take this estimator and we use an importance sampling correction of the distribution. And this is called full importance sampling and suffer from high variance, because you can see that there are a productory of many importance sampling terms. Or what actually we do in deep reinforcement learning is to omit many of these terms, just take the last one. And this estimate is biased, has less variance, but has also a high bias. And this bias increases as much as the distribution shift between the target policy and the behavior policy is strong, is large. And in fact, previous research actually highlighted that off-policy deep reinforcement learning algorithms are ineffective when they are truly off-policy, so when this distribution mismatch is large. So what can we do to recover or to mitigate this issue? I want for a second to pause with thinking on the policy gradient, and let's think on policy evaluation, which is a much simpler problem and has been studied for a long time in reinforcement learning. In policy evaluation, we want to evaluate the return. So one way to evaluate a policy, so to estimate the return, is to take a sequence of rewards and then use this Monte Carlo estimator. As we already told, this way has a high variance and is problematic when samples are off policy. However, a better way, usually, to estimate the value of a policy is to use temporal difference. And temporal difference is composed of many components, let's say. One component is the critic. So we need to define a critic. In this case, for example, the Q function. And we define the Q function in the usual way, for example, as accumulation of rewards from a starting state and action. Then we need to redefine this quantity in a recursive way. And usually we do that with a Bellman equation. Once we have the Bellman equation, we can derive our temporal difference estimator that I guess you are all familiar with. And by using the temporal difference estimator, we don't need any more importance sampling. So if you think, for example, about the DDPG and the update rule of the Q function, there is no importance sampling ratio. Once you found with temporal difference your Q function, you don't need any more, for example, to sample trajectories or sample states, but you can just use the starting state distribution and evaluate your return by querying your Q function on the starting state and the starting actions. And in this way, you can once again avoid important setting. So I think this is one of the main reasons for which in most of deep reinforcement learning algorithms, we are relying on critics, on Q function, value function, or advantage functions. So to repeat once again, when samples are of policy, temporal difference technique usually offer a good trade-off between bias and variance. They are usually superior to Monte Carlo estimate. So at this point comes the idea, why don't we use a temporal difference for policy gradient estimation? To do that, we need to introduce a critic. And we call this gradient critic. The gradient critic is defined in our work as the gradient of the Q function with respect to the policy parameters. I want to do any derivation, so you need to trust me on this. But this means also that this gradient critic, it is equal to accumulation of discounted gradient terms, G, starting from a defined state induction pairs. And you can get them with, for example, your interaction with the environment. And until now, we did not have really nothing helpful yet. But you can have something helpful by introducing also a Bellman equation. So the gradient critic can be redefined in recursive terms by this equation, which we call gradient critic. And that relate the gradient critics with a recursive formula. So you need once again to trust me that this formula is correct, that it is coherent with how I define the gradient critic. And this Bellman equation maintains all the properties of classic Bellman equations. So this guy is again the same guy that we defined before, and this immediate critic is what we previously defined in previous slide. So once again, we can see that we introduced a gradient critic, we introduced a Bellman equation, and we are now ready to use these components to define a temporal difference estimator to estimate our gradient critic. And so we get rid of important setting when samples are of policy. And furthermore, when you take the gradient of the return, you can frame this as an expectation on the starting state distribution of this quantity. And this allows, once more, to get rid of the important setting. As you can imagine, this expression has a low variance because we are just querying this function on the starting state induction. And the bias basically will be defined by how much bias has the temporal difference in approximating our gradient critic. So we don't need important sampling anymore if we use a temporal difference. And furthermore, this is something that we found in the theory. When the critic is linear and features are, let's say, good enough, we can even have an unbiased estimate of the gradient critic, and therefore of the policy gradient. And I think our work is basically the only work able to find an unbiased estimate without using important setting. So up to now, just spoke to you a bit in a theoretical way. I want to show to you how could be an algorithm that uses temporal difference to estimate the gradient of the policy. So here we have the classic, let's say, temporal difference of the Q function. So you can estimate the Q function using temporal difference. And then once you compute your Q function, you estimate your Q function, you plug in this expression, and you use this expression to derive the temporal difference update of the gradient. Once we have this estimator, you can finally update your policy. In our work, we decided to introduce a new hyperparameter called lambda. When the lambda is very close to 0 or 0, basically we have the update rule that I I already showed you. So you have here the starting state distribution. And this means that you are not using important sampling. This estimator has low variance and sometimes is also unbiased. When lambda is equal to 1, we go to the opposite side of the spectrum and we use a Monte Carlo. And as I already told you, this estimator has a high variance because it's a Monte Carlo estimator, and also is usually biased because you are not correcting the state distribution shift. And in between 0 and 1, you have a mixing of the two techniques. So I want now to show you one of the experiments of the paper, so we see how it works, and then we will have some discussion. So in this experiment, we considered MVP by Esan Imani in 2018, and this simple MVP is very challenging for off-policy gradient estimation. It has a state aliasing, which makes the estimation difficult. And we decided to use LSTD, so the least square temporal difference, to approximate both the critic, so the Q function and the gradient critic. On the x-axis, you see our hyperparameter, and I remind you that when our hyperparameter is very close to 0, we are basically fully relying on our gradient critic. While when the hyperparameter is close to 1, we are relying on the classic estimation. Here on the x-axis is instead the performance, so the return. And in this experiment, we can see that when we are using the gradient critic, we obtain highest performance. And very interestingly, even by using a little, let's say the gradient critic, we still have a strong improvement of the performance. While when we don't use the critic enough, or we don't use it at all, there is a sudden drop of performance. So in short, what I want to communicate to you is that this temporal difference technique has a potential, at least, for estimating the policy gradient with off-policy samples. In our paper, there is much more. So there are other experiments, ablation studies, and error analysis. And you can check out, if you want, the paper for more details. And then I wanted to tell the personal news that Rupam already told you, so I will move soon to Innsbruck. And has been a really great time. So I've been here 1 year, a bit more than 1 year. Has been a great time. I've learned a lot. I wanted to thank my advisor Rupam and all collaborators, colleagues, and friends. And of course, I really hope to keep collaborating with you. And if you want to collaborate on this project or on other projects, don't hesitate to contact me. Thank you very much. Any questions?
Yes, sorry. You refer to that quantity G as the immediate gradient, and I know it's equivalent to Q pi, like nabla log pi, whatever. But is that like actually the gradient of something, like a particular, like the expected value Q, or I'm not quite sure.
I think we go to the first slide. This is not very slow, sorry. So this guy is the usual guy that you have in your policy gradient. And I call it immediate gradient because the gradient of the function or the gradient of the return, if you want, is composed by the summation of all these quantities. So I don't know exactly what this interpretation is. You can think actually as the impact of changing this single action, basically, in your MVP. And then you need to compose by looking at the change of all action for all the states in your MPT. So I guess this is the simplest interpretation I can give it. Thanks.
You said that when you use TD, you don't require importance sampling.
Yes.
So I got confused. Is it like Q learning because TD requires importance sampling, right? Like SARSA would require importance sampling.
Yes. So it depends how you do things. So okay, now let's go to the thing. Okay, it depends how you do. So in SARSA, you are using the action that you use in the environment, and so you need to use importance sampling to basically correct the probability of this action A prime. When, for example, you use a DDPG or SAC, what you're actually doing, you're sampling directly from your target policy, and therefore you don't need importance sampling.
I see. And how would this work in gradient critic, your algorithm?
It works exactly the same, right? So, so here, so if you imagine this instead of a Bellman equation, if you imagine like that you want to minimize the mean square error of this guy, you sample this guy from the target policy, and you sample this guy from the target policy too.
I see. And lambda is another functional approximator.
No, lambda, it is just used. So imagine that you're able to approximate this guy. Then lambda, it is needed to basically mix this gradient critic with the classic gradient estimator. It's not a third like function or anything like that.
So one of the slides you said the value function is linear, and I think the features are good enough.
Yes.
Then you have unbiased estimates. What does it mean for the features to be good enough?
Yes, good question. So in our paper, to make the error analysis, we need a strong assumption. So we assume that we have a linear gradient critic, a linear Q function. And what you can think, so there are a bit more details, but in practice, what I can tell you is that if the function, for example, if the Q function is representable in your functional space, then temporal difference will converge to the right solution. And this will be exactly the same for our gradient critic. So if the feature allows you to represent the gradient critic, then the temporal difference will converge. Yeah, thank you. Yes, please.
Oh, you introduced this hyperparameter lambda in your algorithm, and then the graph kind of showed that like if it's 0, then it does really well, and then it drops off. Do you see like a little curve on other experiments that you see, or is it always just to?
So what I think, so we did, unfortunately, the experiments were maybe a bit too simple. So we always used like simple MVPs, like 10 states, something like that. And in our experiment, it always resulted that lambda close to 0 was the best. I think that in a more complicated scenario, for example, when the policies have a lot of parameters or things like this, the temporal difference might have too much bias, and there might be a sweet point where the bias of the two approaches combine its best, and there is less variance of the Monte Carlo. Thank you. Yes, please.
I would like to make a comment and see what's your thought about it. So you derived your critic program function by just looking at the expression. It's a standard way to derive the gradient formulas, the expression for the gradient by starting just differentiate all the sides of the Bellman equation. And then you arrange the terms, you see what is the gradient should satisfy. It is going to satisfy another similar, the same Bellman equation with a different first stage rule. This happens to, this is the same standard method would apply to both discounted problem and the average reward problem. For average reward, it's also simpler like this way. So by looking at Bellman equation for that gradient, or actually you just think like even simpler, so you need have a one-dimensional data, so you look at the derivative, and it will just get one value function. And then in that case, you look at it, it's the same Brownian equation, and you just read out what is the derivative or gradient, because it's the same problem, it's a change the percentage rule. So it's actually a standard way to derive the expression of a gradient this way. So that this would be going in the opposite, actually. I mean, just I just want to say it's this standard way goes opposite toward compared to the direction you get.
Yes, so there are many different ways to derive these things. You can also obtain actually slightly different Berman equation. So we actually derived in the way that you are describing in the paper. I think that for the presentation was better to present in this different way. But you can derive it in different ways too. There are different possible derivations, and they basically gives you the same result. Thanks. Yes.
And when compute the gradients, you actually only compute the gradient for initial states and initial actions. Won't that be a damage in neural networks because we don't have a chance to learn the representation for other states?
Yes, very good question. I think I went a bit too quick on that. So this gradient critic represent or try to predict the accumulation of discounted gradient. So it contains information about the future. That is why you need just to use the first state. And you don't damage anything. Actually, if you have a good, let's say, unbiased estimate, you will have a better gradient. Thanks.
Yes, I was wondering when you learned the gradient critic, in what like distribution do you sample the state from?
So this is another good question. So up to now we are using the same state distribution, so the behavior state distribution, which it is a bit more problematic for temporal difference learning. And maybe in the future we will consider to try to correct this distribution to have better estimation. But I think it's always a matter of trade-off. Like on one side, you will have higher variance and less bias. Yeah. Thank you.
There is a question in the Zoom.
Yes,
sorry,
I have a question. I have a question
Richard.
about the computational complexity of the gradient critic. Seems to me it's just an order bigger than the conventional Q-learning or TD, which is order linear in the number of features.
Yes, so I think that the complexity is just basically multiplied by the number of parameters of the policy. So it basically this equation, it is basically a vector equation, and you can see this as n scalar equations that you are solving, and this n it is equal to the number of the policy parameter. Or if you want to apply it on a subset of the policy parameter, you can reduce the complexity. And actually, it said that from a computational perspective, this is not really problematic because you can parallelize the computations. They are not dependent, so you can just use a GPU and use that hardware support.
Well, the complexity is n squared. You just said it's quadratic, and yeah, so it's like LSTD rather than like TD. It's one order more complex than Q-learning and TD.
Oh, it depends. So we have two sets of experiments. One, we use LSTD, and yes, in that case, it's quadratic. But we also have a version that has online estimation, and in that case, I would say that the complexity is linear.
The complexity of this algorithm is quadratic because you have n equations, and each equation involves n terms. It's an n squared method. That's okay, but yeah, I wouldn't say it's the same complexity as the order n methods.
Okay, I need to think about that. I don't now see why it is a quadratic. I need to think
Thank
about
you.
it.
Thank you.
Thank you. Yes, please.
The experiments that you've done was like linear function approximation.
Yes, we also have experiments with small neural networks as well in the paper. Yeah, I should put it. Yeah, thanks.
We don't use important sampling, does it mean when you estimate your Q and gamma, you are both using TD0 or else TD0?
Can you repeat your question? Sorry.
So you need to estimate the gamma, you also need to estimate the Q function. And
Yes.
you mentioned you are not using important sampling, so this seems to mean that you are using LSTD0 or
Yeah.
TD0 for this, so you are not using multi-step gamma equation, you either estimating Q or gamma. Am I right?
Yes, yes, and even this one, I would say it is an implementation choice. So you can choose to use like eligibility trace or n-step estimators as well. Yes.
Because if you use a single step, it tends to have higher bias.
Yes, that's true. Yes. Thanks. Okay. Okay, thank you very much.
Yes, thanks.